let's summarize now the key topics and points from week 4. And of course, this is the week where the weirdness really begins here. And remind ourselves that it all comes from Einstein's two postulates, that he took the principle of relativity to be true, the principle of light constancy to be true. When you put them together, the conclusion is that the speed of light is constant for all observers, that no matter how a flashlight, a light source would be moving, whether you're moving toward it, it's moving toward you at some angle or whatever. We didn't go into the whole proof there, but essentially argued that based on Einstein's two postulates, speed of light is always constant. So this week then, we've been working out some of the implications of that. And we started with, in Einstein's famous phrase, the idea that time is suspect, which led us to the idea that simultaneity is relative. If you have two inertial frames of reference, inertial being constant velocity with respect to each other, and you have two lattices of clocks in each one, say Alice and Bob, they each have their lattice of clocks, their system of clocks in measurement. Everything is synchronized for Alice, everything is synchronized for Bob. The fact that the speed of light is the same for both of them leads to some weird results. So just remind ourselves of the basic diagram we used. Obviously, we won't go into all the details here. You can go back and watch the video lecture for that. But theme of relativity, simultaneity, and then also this idea that leading clocks lag. So let's just quickly remind ourselves about that. We start off with this situation here, an imaginary, say, Alice's ship with a clock at each end and some sort of device that could shoot out either paintballs or light pulses. If Alice's ship is stationary, then, and she shoots out whether it's paintballs or light pulses, clearly if this little device is right in the center for her ship, she will see the two paintballs, light pulses, hit the clocks at the same time. So assuming her two clocks are synchronized, and when the, say, light pulses hit the clocks stop, or you take a photograph at that point, then both of these clocks will read the same thing. And Bob down here, using his lattice of clocks, we get the same result. Everything is stationary here. Nothing is moving. Then we put it into motion. So we said, okay, now let's let Alice's ship, say, be moving to the right, positive x direction, with a velocity v, speed v. And then we analyzed what happens in that case with the paintballs, one paintball going that way, one paintball going that way. The velocity of the ship gets added to this paintball. So even though this clock, once the paintball is released here, it's sort of halfway in between here on its way over there, this clock is moving away from it. And what happens, though, is the velocity v gets added to the paintball velocity. So if the paintball velocity was u, we saw that it was u plus v. And similarly for the paintball going the other direction, when it's in between there, because of the motion of the ship this way with our little paintball expulsion apparatus or something like that, that shoots them out this way, then it was u minus v, the shooting speed of the paintball minus the speed of the ship going along here. And so even though this clock is coming toward that paintball, this paintball has a lower velocity than that paintball, and they end up hitting simultaneously. So that was the paintball case. But we saw when you have the case of light pulses, then the light pulses in between there travel at speed c. The velocity of the ship does not add on to the light pulses. This is the whole idea of the constancy of light, of the velocity of light, the speed of light, that it's always c, no matter what's happening. And so even though it seems like intuitively, because our everyday experience, if Alice's ship was going that way, the velocity of this light pulse going that way should be c plus v. It's not. It's simply c. And this one is not c minus v. It's simply c going that way. So what that means from Bob's perspective now here, let's take a look at Bob's perspective. He's watching Alice's ship go that way. This clock is receding away from this light pulse. Obviously, light pulse is going faster, so eventually it will catch it, but it has to sort of run ahead to catch it up here, whereas this clock is heading toward the leftward going light pulse, the result being Bob will see the rightward going light pulse hit this clock later than this light pulse hits this clock. Or say perhaps a better way is that this light pulse hits first, and then a little bit later that light pulse hits that clock. Well, what's so strange about that? Well, consider it from Alice's perspective, her frame of reference. She's at rest as far as she's concerned. She shoots one light pulse out one way, one light pulse out the other way. They're both with velocity c, identical velocities. She will see this light pulse hit the clock. Let's just say it hits at t sub a here on her clock. And this will also hit at t sub a. And she's going, hey, no big deal. Bob, on the other hand, is saying, wait a minute, Alice, something's wrong with your clocks. Because Alice says, hey, my clocks are synchronized. They're fine working order. Bob is saying, though, as I observe it, I see this light pulse. Actually, let's do the left one. Hit this clock first, and then a little bit later, this light pulse hits that clock. Take a photo. They both take photos of that instant. Clearly, they have to agree that when this light pulse hits that clock, it's t sub a. When this light pulse hits that clock, it's t sub a. They agree on that. But Bob's saying, according to my clocks down here, my lattice of clocks, this one hits first, and then this one hits second, which means, Alice, your clocks are not synchronized. Okay? They're out of whack. And then Alice can actually do a similar analysis and argue that Bob's clocks are out of whack. It's his problem that is causing this discrepancy. Okay? So the point being is, what seems like should be simultaneous events, these two light pulses hitting these two clocks, Alice thinks they're simultaneous, Bob thinks they're not simultaneous. Assuming, obviously, that v here, the velocity is high enough such that you start to see these effects. The effects occur no matter how big the velocity is here. It's just that the speed of light is so great compared to our normal velocities, the actual effects are so small we don't see them in everyday life. But get up near the velocity of light and you start seeing these effects. So we talk about the relativity of simultaneity. We also talked about this idea of leading clock's lag, because think about this a minute, that as Bob sees Alice's ship going by here, this is the leading clock. Okay, she's going that way, Bob's observing it, and this is the rearward clock, the lagging clock, say. Well, it's not called the lagging clock, just the rear clock. So, as we just argued, Bob sees this one hit this clock first and sees, oh, hey, that's T sub A. And then a little bit later, he sees this one hit that clock, and then that clock reads T sub A. In other words, this clock, as far as Bob is concerned, reaches T sub A first, and then the leading clock reaches it a little bit after that. In other words, from Bob's perspective, from his frame of reference, observing Alice's ship, the leading clock lags a trailing clock in that direction. And later on, actually, next week, I think it is, we'll look at that quantitatively. But for now, we can see qualitatively leading clocks lag. And it's all based on the fact that the speed of light is the same for all observers. So you get relativity of simultaneity, that what's simultaneous in one frame of reference, inertial frame of reference, is not necessarily, is not in general, in another frame of reference, and this whole idea of leading clocks lag. So that was time as suspect. Then we looked at this case of the light clock and discovered that there's this time dilation effect. So let's just briefly remind ourselves. We have a stationary clock here. The light clock had two mirrors. We bounce C up, a beam of light up, and a beam of light back down again. So that's one tick of the clock. Up and down is, or tick-tock if you want to do it that way. And then we said, okay, let's have two identical light clocks, and we'll keep one beside us here. Maybe Bob has that one. And then we'll give another one to Alice, and side by side together, they're in perfect sync, perfect working order. And then we give one to Alice. She gets on her spaceship and travels by Bob at some velocity v. And so Bob then can see his stationary clock right here. He's at rest with respect to his frame of reference. He watches Alice's clock go by and takes 3 snapshots. So here's snapshot 1 of the clock, snapshot 2, snapshot 3. And he sees, clearly he has to see the beam of light hit the top mirror. Because Alice, in her frame of reference, in her spaceship, as she's traveling along, but as far as she's concerned, the clock is right here. It's just going up and down, hitting the top mirror, bottom mirror, top mirror, bottom mirror. So clearly, Bob has to see essentially the same thing. In other words, he has to see it hit the top mirror. And so the only way he can do that is if, from his perspective, the beam of light travels a diagonal path up to the top mirror, and then third snapshot, he sees it back down there again. And clearly then, one tick of the stationary clock, Bob's stationary clock next to him, is faster than one tick of the moving clock, or really the way we often say it is the moving clock runs slow. One tick on the moving clock takes longer than one tick on the stationary clock. Now, and we mentioned this at one point in one of the video lectures, you have to be very careful how you say this, because often it's said, hey, if you move near the speed of light, your time runs slow. And maybe if you can get close to it, time may even stop if you get to the speed of light. Can't quite get there, but say close enough, time essentially stops. That's not quite true, because Alice, who's in the spaceship going, say, near the speed of light, her light clock is working just fine. She notices nothing, right? But it's Bob observing her clock that he says, hey, Alice, if they got back together again, your clock ran more slowly. And this will be one of the key points when we look at the twin paradox later on in the course. Okay? And we did a little quantitative analysis, and we found that the elapsed time on a moving clock, delta capital T on a moving clock, elapsed time is 1 over gamma times delta T on the clock at rest, the stationary clock, where gamma, the so-called Lorentz factor, is 1 over the square root of 1 minus v squared over c squared. And we also explored that a little bit more in one of the video lectures, a short one, just plugging in various values of v to see what gamma would be like. And we found that v has to get pretty big, up around half the speed of light, maybe 0.3, 0.4 the speed of light. You see some noticeable effects, but not until then does gamma really get much bigger than 1. And we noted that gamma is always greater than or equal to 1. If v is 0 here, then both our clocks would be just stationary next to each other, and gamma would be 1, and delta t of the moving clock, elapsed time on the moving clock, would be the same on the stationary clock. They'd both be stationary. But put one into motion, and the elapsed time on the moving clock will be less than the elapsed time on the clock at rest, because gamma is always greater than or equal to 1 here. As for any positive v, any v at all, really, any value of v here, this in the denominator, as long as v is not 0, will be less than 1. So 1 divided by something less than 1 gives you a quantity for gamma greater than 1. So again, moving clocks run slow. The elapsed time on a moving clock is less than the elapsed time on an identical clock at rest, because gamma is always going to be greater or equal to 1 here. So like 1/3, if gamma is 3, that'll be 1/3. The moving clock, for every, if the, say the clock at rest ticks through 9 seconds, the moving clock, if gamma is 3, will tick through 3 seconds. So a substantial difference there. Okay, so that was the idea of time dilation. Time slows down for a moving clock, but it's not the person who's actually doing the moving who observes it. It's the person who is observing the person moving that their clock runs slow. And it's in common language when people talk about this, they often get that mixed up. They assume that, moving clocks run slow, so the person who's moving, if you get near the speed of light, will actually feel like they're aging more slowly. Their clocks will run more slowly. In actual fact, it doesn't work quite like that. Then we moved on and saw that, well, there's something weird about time. Time is suspect. We also learned that length is suspect. We talked about the length contraction effect. Did an analysis like this. Just to remind you of the picture we drew here. We had Alice, and just one clock for Alice, and say her spaceship, or just sitting there, right? And here comes Bob by at some velocity v. And he has his lattice of clocks going along there. Alice, of course, has hers too, but we just need to focus on one of her clocks for this analysis. And the idea is Alice is going to measure the length of Bob's spaceship. So he's coming by at velocity v, and when the front of his spaceship gets right to her clock, she takes a photograph and notes the time on her clock, and then waits until the end of Bob's spaceship gets here, takes another photograph and notes the time on her clock on that photograph as well. And then they also note the time on Bob's clock. So photograph at the beginning on this clock of Bob's, and then as this one comes along, take a photograph of that one and note the time on that. Turns out they get different answers. And so it's a question like, well, who's wrong here? And each of them points to the other one being wrong. Because Bob, think about Bob's perspective here, he's at rest in his frame of reference. So really to him, Alice is moving that way. And when he looks at her moving clocks run slow. So he sees her clock running more slowly than his clocks. And so he's saying, well, that's the problem, Alice. Your clock isn't working right. My clocks are in fine working order. Compared to my clocks, your clock is running slow. And that's why you got the wrong length for my ship. Meanwhile, Alice, her perspective, of course, is Bob is coming by her with this velocity, and she sees it slightly differently. She actually is, for Bob, he's using two different clocks to measure the length. He notes the time here, and then he knows the velocity, v, he notes the time when he gets to there, and therefore the difference in times the velocity gives the length. And he says, you know what's going on? Or he says Alice's clock is running too slow. Alice, looking at Bob's situation, his last clock says, Bob, it's not my problem. My clock is in fine working order. It's your clocks. You think they're synchronized. Remember, leading clocks lag. She says, your leading clock here is lagging this clock. They're not synchronized. No wonder you're getting the wrong answer. Okay? So they get two different answers, and they explain it in different ways, but ways that are consistent with our results from the special theory of relativity. And quantitatively, then, we showed that the result is that the length of a moving object, okay, length in the direction of motion, is if you observe that moving object and you measure the length, so sort of like Alice measuring Bob's moving spaceship here, it will be 1 over gamma factor again, greater than 0, times the length at rest. In other words, you say, okay, Alice says, I want to figure out Bob's ship here, what its dimensions are, and so Bob comes in, they sit down, they both measured at rest, they get one value, but then when he's flying by with some velocity, and Alice takes the measurement again, she will get a shorter result for that length. This one, like gamma might be 3, so it would be 1/3 times the length at rest. So length contraction. The length of a moving object, when you measure it, is less than you'd measure it when it's at rest. And when it's at rest, sometimes we call that the proper length, or just the rest length. Proper length, again, as I mentioned in the video lecture, it's not a misnomer in a sense, but it's a little confusing because it then seems like other lengths are not proper, improper lengths. But it's just an idea that the length at rest versus the length when an object is moving, measured when it's moving. And later on in the course, we'll see, because you could ask, if this is length contraction, does Bob feel that contraction in a sense? And the answer is no. The contraction is real in the sense that Alice is measuring according to proper techniques, but just because of the relativity of simultaneity and how time works, you get a difference in the measurement of lengths, whether something is moving or at rest. So that's length contraction. Then we considered what is not suspect. So let's erase a little bit of what we have here. And just remind ourselves a couple things about that. So what is not suspect? Because we have, well, time is suspect, length seems to be suspect here. What else is suspect or not suspect? And so we had an argument to say that transverse dimensions are not suspect. We looked at the train car with the train tracks, and we looked at both Alice and Bob's perspective, and we saw that if the width of something moving along this way contracted, we get contradictory results. One of them would see the width getting narrower of the train car. One of them would see, so say Alice would see if it was width contraction, as Bob went by in the train car, Alice would see the width getting narrower, and therefore the train would fall through the tracks. From Bob's perspective, sitting in the train car, he'd see the tracks coming toward him, So if there's a width contraction effect in effect, then he'd see the tracks getting narrower, and so the train car wouldn't fall through the tracks, so the wheels would sort of go off the end. So you have two contradictory effects there, the conclusion being that there is no width contraction. And then we did a similar argument for the height of the train car versus the tunnel. Again, it concluded no width contraction, no height contraction, or anything like that. It's only in the direction of motion that you get the length contraction effect. So those are two things that were not suspect, width and height. But we also talked about the invariant interval. It took a little more doing, maybe not too much doing, to show this result. But the idea here is if you have two events and you measure the location and time of those two events in different frames, even though, say, Bob and Allison, we had Chris as well, they all disagreed exactly where the two events occurred and the time between the two events. We use flashes of light in a light clock. But this quantity, if we did c squared, t squared minus x squared, that is always a constant. And it actually has to do, we still have a little light clock here, as you may remember, it has to do with the height of the light clock was the same for Alice and Chris and Bob. The transverse dimension does not get contracted or expand or anything like that. It's constant, and that's really where this result comes from. So what that means is, for Alice, say, speed of light, c, is the same for all of them. Alice would have a certain time, t sub a, between two events, and a certain distance between two events measured in her frame of reference. Chris could take similar measurements, and she would also get c squared tk squared minus xk squared. She'd have different values for the time between the events and the distance between events than Alice would, but you get the same result. When you do this calculation, you'd have the same answers there, and the same thing for Bob if we did a version for Bob, x sub b squared equals constant, the same constant as well. So all these things are the same. The example we actually did had Bob being the distance between events was 0, so sometimes you just get that. But in general, time and distance between two events, between various inertial frames of reference, this value, this quantity will always be a constant. We call it the invariant interval, and it'll be useful for us later on with the Lorentz transformation. And then finally, we did an example with a muon. Because you can ask, is this really real? Does this stuff go on? And muon is a classic example. It's a subatomic particle. What happens is, as cosmic rays come into the atmosphere, they hit some atomic nuclei up there in the atmosphere. And cosmic rays, very high energy particles coming in, probably generated in supernova explosions elsewhere in the galaxy. And so we're always getting cosmic ray particles coming through. Some of them hit things up in the atmosphere, create muons and other particles. Some of them actually make it down to Earth. Maybe you've been at a science museum before where they had a cosmic ray detector, sort of spark gap type thing, and the cosmic ray going through would generate sparks, so you can actually sort of see their paths go through. Anyway, that's a side point there. What about the muon? Well, as these cosmic rays come down, remember, you get these muons being generated at about 10 kilometers high in the atmosphere. And turns out, we can study the muon in the laboratory, and the muon has a lifetime of about 2.2 microseconds, something like that. A very short lifetime, millionths of a second, 2.2 millionths of a second. This is mu for microseconds there. And so these cosmic rays generate these muons. Say, here come the muons, and here we are down on Earth. And it turns out the speed of the muons generated is very, very high, about 0.998 times the speed of light, so very close to the speed of light. And at that speed, turns out that gamma, the gamma factor, Lorentz factor, is about 15. And so the question is, okay, this is the lifetime, you could say the proper lifetime, the rest lifetime. In other words, if the muon is at rest, it lasts 2.2 microseconds. At this speed, 0.998 c, if it lasts for 2.2 microseconds, it can only go about 600 to 700 meters. Okay, so if it's generated 10 kilometers high in the atmosphere, it shouldn't be able to get down to Earth. Right? It can go about less than 1/10 of that way, 600, not even 1 kilometer. And yet we see the muons down here at the surface of the Earth. So somehow they get from 10 kilometers high, we know that's when they're generated, a lot of them, and they get down to Earth. So what's going on here? Well, we can explain it and get the correct result only using special theory of relativity. The idea is this. We're observing the muons. Its lifetime is 2.2 microseconds in the laboratory when it's at rest, essentially. But when it's traveling at a high velocity, what do we see? We observe its internal clock, as it were, undergoing time dilation. And the time dilation with gamma 15, it means it's about a 15 times factor for the time dilation effect. In other words, we observe the internal clock of the muon as it's comes screaming down towards us at 0.998 c, that its lifetime lengthens by 15 times. And if you work it out, if you lengthen its life by 15 times, it's moving at this velocity, it has just enough time to make it all the way down to Earth here, instead of ending up someplace up here and decaying into other particles is what it does when its lifetime is up. This is average lifetime there. So that explains how it gets down to Earth. And then also, but what about from the perspective of the muon? Because you could say, well, let's ride along with the muon if we want, if we could. And it has its sort of internal clock ticking away. There's no time dilation effect in that case. It's in its rest frame of reference. It's going to live for 2.2 microseconds. How in the world, from its perspective, does it get down to Earth 10 kilometers away, the surface of the Earth? Well, here's sort of the ingenious part, or the amazing part of special theory of relativity. It doesn't have time dilation, but it does have length contraction going on, not for itself, but it's seeing the surface of the Earth rushing up towards it in its rest frame of reference. Because the surface of the Earth is coming towards it at 0.998 c, gamma factor 15, it sees that length to get down to the surface of the Earth not to be 10 kilometers, but to be 1/15 of that. In other words, about 600, 700 meters or so. So it only, in its frame of reference, it only survives for 2.2 microseconds, but it doesn't have as far as to go to get down to the surface of the Earth. Whereas from our perspective on the outside of the muon, it has to go 10 kilometers, because that's what we see in our rest frame of reference, but it lasts 15 times longer, and therefore is able to get there. So that's quick, relatively quick maybe, summary of week 4, where we saw some of the weirdness begin. And these are things that we're constructing mental models here. And mental models are very different from how our ordinary experience goes. And therefore, it takes some time to sink in, to play around with these things, take notes, work through it, see if you can do the muon example, watch the video lecture, and say, okay, do I understand the muon example? Work through it. Some of the other examples we did as well. Even from my own personal experience learning this, it takes time to sink in and become familiar with it and comfortable with it enough so that, you sort of understand that there. Remember, again, I don't know if we mentioned it recently, but we start off with the course, one of Einstein's quotes about the struggle to understand. And certainly at times there can be a struggle to understand some of these things, but if you persevere, work through it, and hopefully gain some insight in that as Einstein put it, it can be even an ennobling and enriching experience. I hope we're getting a little bit of that as we get into some of these weird things with the special theory of relativity.